Good afternoon, everybody. Welcome to this session of structural engineering, design and detailing. As in the previous class, I had explained you all about the importance of steel structural members, and I had even explained you all about the typical components of a plate girder and all the connections related to this plate girder also. I had explained you all about the flange splice and the wedge splice and the stiffeners. What is the importance of the stiffeners, vertical stiffeners and horizontal stiffeners. Today specifically we will be seeing the design steps involved in the making of the plate girder. See, this is a very important problem. I request all of you all to please go through these design steps. As per the university norms, it carries about 15 marks. So this is a very important topic. I request all of you all to please follow this. We will be seeing today all the design steps involved for making of the plate girder. So, the design steps the first step what we will be seeing is what is the load acting onto the plate girder and what is the span given for the plate girder. See, normally the load which comes onto the plate girder, it is a UDL, uniformly distributed load. But in some cases there are chances of some point loads also coming onto the plate girder. So we will have to determine what type of load is coming onto the plate girder. That is very essential because the next step which will follow this is related to this only. So it is very important we have to identify what types of steps, what types of loads are given that are coming onto the plate girder and what is the span given here. So the step 1 will be determining the load coming onto the plate girder. And the span given. So basically first what we will have to see is we will see what is the load coming onto the plate girder and what is the span given for this basic problem here. So as it will be a UDL and sometimes a point load can also come here. So we will see that specifically, then we will see what is the span given, and therefore next we can go for the next step. Hope you all have understood what type of load come onto this plate girder. So it is a UDL. We will see what is the step 2 coming. So as I had told you, the UDL will be coming here. Step 2 we will be seeing, we will be finding out. We will be finding out the maximum shear force and the bending moment coming onto this. So the maximum shear force and the maximum bending moment, what will come onto this because of the UDL or a point load, we will be seeing that. As you know, when if you have a simply supported beam, if we take a simply supported beam and this is the UDL, uniformly distributed load, let us say W kilonewton per meter, and let this distance be L, A and B. As you know, the maximum bending moment coming because of this UDL is WL square by 8. We can solve it. You can just see here. We'll have to find the reactions and we'll find the moment, and you'll get what is the maximum bending moment that will be coming. As you know, you have already learnt it in your previous years in the shear force and bending moment topic. The maximum bending moment that comes because of the UDL is WL square by 8. Okay, fine. And the maximum bending moment that you get for a point load is WL by 4. So depending on what type of load is coming, we can decide what will be the maximum bending moment and what will be the maximum shear force that is coming onto the span. Now this is very important because this is related to the next step, as we will be finding the depth of the girder. So second step also, hope that is clear with you. Second step also must be. Next in the step 3 we will be seeing, we will be determining the depth of the, we will be determining the depth of the web. Now let us see, the step 3 will be determining the depth So next we'll have to find out, determine the depth of the web using the equation. Now the equation given is D is equal to mk by Fy to the power of 0.33. As I told you, what is m? M is the moment that we have got, and what is k? K is a constant here. Here we'll have to assume k. It is either we'll have to assume it as 100 or 150 or 180. Basically, k is a constant here, and Fy, it is the yield stress. Fy is the yield stress. So you can see here, m is the moment, and next, as I had told you, k is constant. You have to either assume it as 180 or 150 or so on. And next, Fy, this is the yield stress. So you have seen here, we'll be getting the depth of the web. Depth of the web will be gone. We'll be getting it here. Next, depending on this, next we'll have to find out the thickness of the web. Even we have an equation for that also. Let us see the fourth step. Let us see the fourth step. We'll have to find the thickness of the web. Now we'll have to find the thickness of the web using the equation. That is also, we have an equation for that. T is equal to m by Fy in k square. Thickness m by Fy k square to the power of 0.33. Okay, as I had told you, m is also the moment, Fy is the yield stress, and k is the constant. But here, as you can just see here, I have just not rubbed this step because these are connected together. This is the thickness of the web, this is depth of the web, and this is thickness of the web. So here depth m, moment, k is the constant what we are getting, Fy is the yield stress, and to the power of 0.33. Okay, the same way here we'll be getting the thickness of the web, that is moment, m is moment, Fy is the yield stress, and k is the constant what we are getting to the power of 0.33. Now what we have got, this is our I section. This is our I section, and this is the web what we have designed here. In web now we have got this depth dw, and we have got this thickness also tw. So now we have determined the thickness of the web as well as depth of the web. Now what we'll have to do, we'll have to determine what is the size of the flange here. We'll be seeing the size of the flange here. Now we'll be determining the flange. For that, hope this is clear till now and you must have understood. Next, the step what we'll have to do is, we'll have to find the flange. Now we have found the depth of the web and we have found the thickness of the web. Next we'll be determining the flange. What are the size of the flange? What size should the flange be? We'll be seeing that now. You can see here, next step will be determining the size of the flange. For that, what we'll have to do is, first we'll have to find out the area of the flange. Now here, to determine the size of the flange, we'll have to find out the area of the flange. Now area of the flange can be found out by the equation A is equal to m by Fy into D minus of, find the area of the A is equal to m by Fy into D minus AW by 6. You can see here, area is equal to m is the moment, Fy is the yield stress, D is the depth which we have got from the previous step, and AW is the area of the web. We have already got the depth and the thickness, so we'll get the area of the web, and then by 6. So by getting the area of the flange, now we can get the breadth of the flange and the thickness of the flange. Now after getting this, AW, I'll just explain. AW is the area of the web. Area of the web. Fy is yield stress, as you know. D is the depth of the web. Now after getting this, next step we'll provide width of the flange. Width of the flange we'll first get we'll have to find out. We have got the area of the flange. Here you can see we have got the area of the flange. Basically, what is the area? Area of the flange is breadth of the flange into thickness of the flange. So here what we'll do is we'll provide the width of the flange 1/3 of dw, 1/3 of depth of the web. So BF is equal to 1/3 of dw here, depth of the web. Now we have got BF. Basically, what is area of flange? AF is equal to BF into TF, breadth of the flange into thickness of the flange. We have got BF, 1/3 of depth of web, we have got BF. Now from area of flange, we have got this from this equation, area of flange, this is area of flange. We have got area of flange. Now we'll just substitute this values and this values and we'll get the thickness of the flange. So till here we have found out, we have already got, we have got this also, breadth of the flange, BF, and we have got this thickness of the flange. We have even determined this as thickness of the web, and this is depth of the web. So now we have calculated everything. We have calculated the I section, we have got the size of the web, as well as we have got the breadth and thickness of the web also. So hope you have understood this equation also. Next we'll have to find out, we have got the size of the web as well as size of the flange. Now we'll be determining the moment capacity. From here we'll be seeing what is the moment capacity of the I section. We'll have to find out this. Let us see the step 6 here, basically step 7 here. Determining the moment capacity. One thing you all should keep in mind, I request all of you all, the code book what we need to design a plate girder, and for the whole of this subject you need is IS 800 of 2007 is required here. You need to have IS 800 of 2007. You all have already used this code book in the previous subject of steel structures. I request you all to please keep this book because it is very important. Determining the moment capacity. Now what is the moment coming? Moment capacity, we'll have to design that. That is given by the equation in the page 73 of the IS code here. See IS code 800 by 2007. In the page 53 it has been mentioned here. MD, it is given in the code book. MD is equal to BB into ZPFY by gamma M0. Now you can see here now what is it has been given in the code here in the clause 8.2.1.2 MD. What is the moment? It has been given here BB. This is the plastic or the compact section. What is there? We'll have to find out this. What is BB? Now to find we'll have see BB is either it is plastic section or compact section. We'll have to see this. And ZP, this is the plastic modulus here, and FY, as I have told you, this is the ultimate stress here, and this gamma M0, this is, you can get it from page 30. Page 30, this is the partial safety factor. We'll just see how to check for a BB plastic section and the compact section, but this is written in page 53. This code has been given in page 53. Okay, you can just see it there in the page 53 of IS 800 of 2007. It has been clearly mentioned. Now to find out BB, what we'll have to do is in the page 18, you can go to the page 18 here. You have to go to page 18. In page 18 it is mentioned here. You can see here in page 18 it has been mentioned here how to, if it is welded section, what we'll have to do, what is for plastic section and for the compact section. It has been given here B by TF. We'll have to find out B by TF. That if it is less than 9.4 epsilon, then it is a compact section. It is less than 8.4 epsilon, it will be a plastic section. So basically BB, and it has been also mentioned in the page 53. When you open page 53, it is mentioned there. You can see here for plastic, one for plastic and compact section. It has been given BB is given as one for plastic and compact section. It has already been given here in the code book. So this is there, and Fy, as I have told you, that is the yield stress, and the gamma m0, this is the partial safety factor. It is given in page 30, gamma m0. You can just see here in page 30, if you go to page 30, it has been given here. You can see here in the page 30, partial safety factors for gamma m, it has been given here. You can see resistance governed by yielding, gamma m0 equal to 1.1, and for buckling 1.1, for ultimate stress it is 1.25. So basically we need it for yielding, that is 1.1. So even this is given in gamma m0 on page 30. Okay, hope you all will see IS 800. This is in page 53. From there you will get gamma m0 in page 30. Now what is ZP? That is plastic modulus. ZP is plastic modulus. Now what is that? Plastic modulus ZP is, how do you get that? ZP is equal to area of flange into CG of flange plus area of web into CG of web. So you can see here, just see the step, moment capacity, BB into ZP, Fy into gamma m0. We have got what is BB, that is 1 for plastic and compact section. ZP, gamma m0, this is a partial safety factor which is given in page 30. And ZP is the plastic modulus. How do you find that? Area of flange into CG of flange and plus area of web into CG of web. So now we have got all these. Fy is the yield stress of concrete. Hope you have understood this step here. Now this step we have got, we have determined all this. Now what we have to see here is we are determining the moment capacity. After putting all these values, we will get some moment here. Design moment we will get here. Now what we will have to see is this design moment should be greater than the maximum bending moment which we had calculated in second step. This should be greater than, MD should be greater than the maximum bending moment what we had got in the step 2. That is important. MD should be greater than MU. Okay, if this is greater than MU, then this is safe. This is safe. That is what we'll have to see it. This is very important. So this is step 7. Hope this is clear. You all must have understood all this. Step 7. Next step, now we have determined the moment capacity. We'll see, we'll have to check for low shear or high shear here. Let's see the step 8, what we'll have to do here now. Now again this step, it is given in page 53. Page 53, if you open page 53, you can, a clause has been given here in page 53. You can see here, when the factor designed shear force does not exceed 0.6 VD, where VD is the design shear strength of the cross section, then the design bending strength should be taken as MD. You can see here, it has been given in clause here in the page 53, VU should be greater than or equal to 0.6 times of VD. Okay, VU should be greater than and equal to 0.6 times of VD. Now what is this VD? It has been given, you can see here, the VD, it has been given in the next page. You can see in the page number 53, it has been given, clause 53, 8.2. After this, what is VD? We will see in the page 59 here now. Page 59, in the code book it has been given. You can see here in page 59, the nominal V should be less than or equal to VD. VD is the design strength. Okay. Now what is VD? Design strength is given by Vn by gamma m0. gamma m0. Now what is this gamma m0? This is partial safety factor. Now Vn, this is normal plastic shear, is equal to Vp, Vn. Now again in the, this is in page 53. This is given in page 59. You can see here Vu should be less than or equal to 0.6 times of Vd. This is given in page 53. Now what is Vd? That is design strength. That is given in page 59. That is given in page 59. You can see here Vd is equal to Vn by gamma m0. Now what is Vp? We will have to see. Vd is equal to Vn. Vd is equal to Vn by gamma m0. Okay? Vn, what is Vn given as? In the code you can see here, it is given as Vn is equal to Vp. This is the nominal plastic shear resistance given here. Now what is Vp? It has been given by, again in the code book, it has been given as Vp is equal to area of the web, AV FYW by sigma 3. You can see here it has been given in the page 59 also. All this sequence has been given. Vu should be less than or equal to 0.6 times of Vd. Basically this is Vu, this is the maximum shear force that we have determined the step 2. Now Vd we will be finding out what is this design shear. The design strength what we are seeing, that is given by page 59, Vn by gamma m0. Now Vn is Vp. It has been given in the code book as like this only, a sequence. So what is Vp? Vp is area of AV. This is area of web. Now this is yield stress of web by root 3. So this should be, now this has been given as, now this should be greater than, this should be, as I have told you, Vu should be less than or equal to 0.6 times of Vd. Now here we have found out the moment capacity in the previous step. Now here we are finding out the check for shear. We are seeing whether it can resist shear or no. This is how we are seeing this. So this is a step 8. Next we will go for step 9. Let's see step 9. Step 9, what is step 9? We will be seeing curtailment of flange plates. Step 9. Now what is this curtailment? As I had told you all in the previous class also, basically what is curtailment? What do you mean by? What happens when we have determined the size of the breadth of the flange and thickness of the flange? Sometimes what happens is the thickness of the flange what we get, it is very high. We get about, you can, just for an example, if we get 30 mm. So 30 mm is a very thick plate and it is not easy to weld that plate. So that time what do is, we take 10 mm size of plates and we fix 3 10 mm size of plates here. 3 plates. So this 30, see this is 30 only, but this each plate is of 10 mm. 10 mm. So it will be very easy to weld these plates. Now what is curtailment is, as I had told you, if we have taken this simply supported beam and this is the UDL coming over it, and see, now this is the maximum bending moment which we are getting here. Sorry, you can just see here, maximum bending moment, not like this. The maximum bending moment WL square by 8 is at the center. That same loading, that same moment is not coming here. The moment will be changing here. This you have different moment, here you have different moment. Now when you put W at the center, we are getting it as WL square by 8. But at the corner edges, the moment is low. For that what we do is, we cut these plates. We cut these plates. So when we place these flange plates, what do is, we cut it like this. So this flange plates can cut depending on this bending moment. Now how to cut these flange plates? That is called as curtailment, and it is being given by a formula 2x1 is equal to L 2x1. Now this you can just see first plate we are seeing for the first plate. 2x1 is equal to L into A1 net by 2x1 is equal to L into A1 net by AF net plus AW of area of web here it is A1 net by AF area of flange of the web AW by 8 here by 8. So this is what 2x1. Now what is 2x1? This is this plate, that is the last plate which we will be cutting here, that is the 2x1 here. You can see here 2x1, this is this plate you can see 2x1, this plate is 2x2. So 2x1, this plate, how much should we cut it? What should be the size of this plate? This much is 2x1. 2x1 is this size. L into root of A1 net by AF net plus AW by 8. This is the same way. What should be 2x2? It is very simple. Yeah, there is no change in it. Just A1 net plus A2 net, AF net plus AW. Now you might be thinking, what is A1 net? 2x1 is this size, as I have told you. 2x2 is this. L is the length of the first plate, length of the length of the span of the girder. L is basically span of the girder. L is span of the girder. Now what is A1 net and what is AF net? That is A1 net is net area of first flange plate. First flange plate. First flange plate means net area, that is the first flange plate. What size I am taking? Either I am taking 10 into whatever breadth of the flange I get, that is the area. Sometimes I can take 12 plate of a size of 12 also. Size of 12 also I can take. It is not necessary I should take only 10. I can take plate of size 8 or 10 or 12 or 14 also. It depends on me. So it will be, the figure will be like this. So this is the first plate, 2x1, area of first net. The same way, A2 net is, what is A2 net is? The second plate, what is this size? This size. I am taking it as 10 mm or 12 mm or 14 mm. It is on me. So I'll just calculate that area. And AF net is the total size of the area of flange. That is the total thickness of flange into breadth of flange, area of flange. AW, as you know, that is this is area of the web. So this step also, curtailment of the flange plate. Hope even this is clear. You can just see it is very simple here. Okay, it is very simple here. We have determined all these. 2x1, 2x2 also we have determined. Okay, 2x1, 2x2. Next, we will go for next step. So we have got, we have done the curtailment of the flange plates also. Now what we have designed, we have seen the moment capacity, we have seen for low shear also, we have done the curtailment also. Now we will see the connection, we will see the design of connection between flange and web now. The next step will be, Now we have determined the flange as well as web, and we have seen whether they can resist the moment capacity and the shear. Now we'll have to see the connection between flange and web. We have to connect this. So the shear steps developed at the connection between flange and web is given by the equation. It is given by the equation. The shear stress is developed there, and it is given by equation. Q is equal to shear force by I into B. Q is equal to shear force by I into B. A y bar, it is A y bar. Okay, now what is Q? This is the shear stress that is being developed at the junction of the flange and web. Shear stress is developed here at the junction of the flange and the web. So that can be got by the equation Q is equal to shear force, which we had calculated before, by I. I is the moment of inertia of the complete section. I is the moment of inertia of the complete section, and B is the width of the section. Here we take it as 1 mm only. A is the area of the flange, that is, and Y is the distance from here, from the CG to the closest section, from here to the CG of the web, from here to the CG of the flange. I'll just write it down. Shear force that is developed in the member, SF is the SF is the shear force developed in the member. That is what we have already calculated it. I is the moment of inertia of the complete section. Okay, moment of inertia of the complete section. Now what is B? Width of the section. Here we will be in the design, we will be taking it as 1 mm width only. We will be taking only 1 mm width here. B, we will be taking it as 1 mm width. So shear force I, moment of inertia, B is the 1 mm width. And what is A now? This is area of the flange. A is area of the flange. A is area of the flange, and Y is, this is the distance of the centroidal axis of the section. Distance of centroidal axis of the section. Of section. Okay, now this is what Q we have got, design of connection between flange and web. This is the connection what we are seeing to design this. Q is equal to shear force by I into B into A Y bar. Now what is C? SF, shear force developed in the member. I is the moment of inertia of the complete section, and you can see here B is 1 mm width we are taking here. A is the area of the flange, and Y bar, this is the distance of the centroidal axis of the section. So this is the 10th point which we have covered. 10th point. So next we will see the step 11, that is design of the weld. We will have to see what type of weld. The step 11 is design of weld. You can see here the design of weld. Now this is given, design strength of the weld is given by the equation, the page 79 it has been given. Page 79, if you open page 79, you can see here design strength of fillet weld. Strength of weld, this is given in page 79. Strength of weld is given here as FWD is equal to FWN by gamma MW, Next in the next step it is given as, what is FWN? FWN is equal to FU by root 3. Here FU, you must understand here, FU is the ultimate stress of the weld, ultimate stress. FU is ultimate stress, and gamma MW is a partial safety factor. FU ultimate stress, gamma MW is partial safety factor. This is mentioned in page 30. You can see there. It depends on what type of weld you are taking, either it is fillet weld or whatever weld is given. You can see that in the page 30 here. So this is the last step. This was the 11th step here. 11th step, design of weld. Now I'll just tell you a short recap. First step was we were seeing what are the loads coming onto the girder. Then we were, and the span of the girder. Next we were determining the shear force. That was step 2, was determining the maximum shear force and the maximum bending moment. Okay. Next we were, then we came for design of the web. We were determining the depth of the web. D we had got, then we had got the thickness of the web also. We determined the DW and TW. Next what we got, then we went for the design of the flange here. We had seen what is the breadth of the flange and thickness of the flange. So till here we had designed the web and the flange. Next what we had done the moment capacity. We had checked for moment capacity. MD we had checked, that was given by the equation. MD we had checked, and the design moment should be greater than the maximum bending moment, as I had told you. That was a step 6 most probably. And the step 7, what was it was? Step 7 was we had seen for low shear whether so VD should be less than or equal to 0. VU should be less than or equal to 0.6 times of VD. That was the next step. After that, step 7 or step 8 it was, we had seen for curtailment of flange plates. We had seen the curtailment of the flange plates. That was the next step. After curtailment of flange plates, then we had seen the design for the connection, design of connection between flange and the web. That was given by Q is equal to SF by IB into AY bar. SF by IB into AY bar. SF was shear force, I was moment of area, and SF by IB. B is the 1 mm width we are seeing into A into Y bar, area into centroidal distance. After that, this is the step what we have got here. Design of the weld, connection we have designed already, and here there is a design of the weld, strength of the weld has been formed. Here now we have, this is how we have completed all the steps. I request all of you all to please go through these steps. See, this is a 15 marks question. It is very important and it is very easy also if you practice it. The problem is just because we don't practice. See, I'll just after writing these steps, I have just told you all these steps in one go. I have told you all the 12 steps in one go. If you are familiar with the steps as well as with the code book, where to use the code book, which page you have to use the code book, it will be very easy for you all. You won't waste the time as well, and you can score very good marks also. I request all of you all to please go through this video. Thank you for we'll be finishing this session. In the next session, we'll be dealing with a problem. We'll be directly doing a problem, and we will be doing one question from the question paper also, previous, which has been given already, and we'll be dealing there. It will be, you will get a very good clarity there. Hope this session was informative to you. I request all of you all to give comments in the comment section. If you all have not understood anything, it will be my pleasure to answer all the questions what you have posted on the comment section. Thank you for that.